This geometry question looks deceptively simple and it has a beautifully elegant proof, but that does not mean that it is easy. And the way that I originally saw this proof, this question solved, used the cosine rule and algebra and all sorts of steps, and I just thought there must be a simpler geometric way to solve this. The question's asking for the area of the small triangle, given that we know that the side length of the larger triangle is 2. And just to note, both of these triangles are equilateral and they're inside of a semicircle. So when you look at this problem, what's the first thing you might think about doing? Now, of course, it would make sense to join up a center of the circles with any points on the circumference, because when we add that radius in, it might just give us some insight or some intuition about where we can go next. And of course, from that, we could calculate the area of the larger equilateral triangle using Pythagoras, knowing that this is a right angle. Because this splits the base of the triangle in half, this length would be 1 and the height would be √3, which is also the radius of the circle. We might not know how that's going to help yet, but it's still good to find out, and it might have its place later down the line. So as you're looking at this, you might be start to think, this triangle here, and we can call it OXB, it kind of looks isosceles, feels like this meets at a right angle, but unfortunately we can't assume in our proof that is true. So we don't know that, and if that were true, and this is 1 and this is 1, it makes the whole question very easy. And the real challenge in this question is proving that this is indeed an isosceles triangle. If we can do that, well, the rest of the question is just finding the area of the triangle, right? So how are we going to do this? Now, since we know that these are two equilateral triangles, this angle is 60 degrees, so is this one. We know that this is √3. One way we could do it is by using the cosine rule to figure out the other side here. But suppose you don't want to do all that algebra. One idea that often helps in these types of situations is doubling the semicircle to create a full circle and reflecting some of the lines into that circle. The only lines we actually needed was the extension of BX. We can construct the line from O to the extension of BX in a way that it forms a right angle. And because we've constructed this, we can choose for it to meet at a right angle essentially. And what this gives us is another triangle. We could call this point Z. So in OXZ, we can figure out these angles. Since we know that it's an extension of BX, so it's on a straight line, this angle will be 60 degrees. And thus, because it's a right angle, this angle will be 30. We know the hypotenuse is 1. And thus, because it's in the ratio 30, 60, 90, it's half an equilateral triangle. So we can work out the other side lengths. So this one would be a half, and this would be √3 over 2. And now from that, we can use Pythagoras' theorem on the triangle OBZ. You know the hypotenuse is √3, so it's going to be √3 squared minus √3 over 2 squared is equal to BZ squared. Let's just take a moment to see where that came from. And then as we go ahead and solve this, we find that it's going to be 3 minus 3 over 4 is equal to BZ squared. So 3, that's the same as 12 over 4. So that's going to be 9 over 4 is equal to BZ squared. Beautiful, both square numbers here. So BZ is going to equal 3 over 2 or 1.5. And because BZ is 3 over 2, that means BX is going to be 3 over 2 minus 1/2. It's just going to be 1. And just like that, we have proven that OXB is indeed an isosceles triangle, and therefore the side length BX is 1. Now we can just finish off this last step, calculating the area of this triangle, knowing that the height is √3 over 2 and the base is 1. So the area will be a half times √3 over 2 times another half. So the area will be √3 over 8. If you like that, drop me a follow and let me know if you find a better method in the comments.